Imagine accidentally shipping like 1 million gallons of dead weight across the globe, just burning through millions of dollars in diesel and freight costs to move something that, you could literally just get out of a tap.
Yeah, which is a total nightmare.
Right. And that is exactly what happens when chemical and process engineers fail to properly do the laundry, basically. Because when you look closely at heavy industry, I mean, pharmaceuticals, food production, pulp, and paper, so much of the engineering really just comes down to one monumental challenge, which is getting water out of things.
It is, it's a massive logistical and economic bottleneck.
Hmm.
I mean, we tend to think of drying as just a simple preservation technique.
Which it is, right?
Well, sure, it is.
Uh,
But on an industrial scale, evaporation and drying are really about optimizing transport and storage. So it is always cheaper to extract a volatile solvent, which, is usually water right there at the manufacturing plant. Then you ship a dense dry powder and let the end user add the water back in later.
that makes total sense. So welcome to this deep dive. Today we are acting as your personal engineering professors. We're looking at a stack of advanced process engineering lecture slides focused specifically on mass transfer.
Right, topic 6, I believe.
Exactly, topic 6. So our mission today is to understand the physics of drying, psychrometrics, evaporation modeling, and how to handle multiple heat sources.
It's a lot of ground to cover.
It really is. But whether you are studying for a major heat and mass transfer exam or gearing up for real-world plant design, we are going to make the underlying mechanics of all these concepts intuitive. So, okay, let's unpack this. We know the economic incentive to remove water, but you can't just, blast a wet powder with air and hope for the best.
No, definitely not.
So how do we actually pull this off on a massive scale?
Well, you start by choosing the right hardware, and that depends entirely on the physical state of your product and, your production volume.
Okay, so where do we begin?
So the baseline is a tray dryer. You basically have this large insulated cabinet where wet material just sits on trays.
It's a big heated box.
Pretty much. A fan forces air over a heater,
Yeah.
and then you have these adjustable louvers that direct that hot air across the product.
Yeah.
It is a batch process. But the critical engineering challenge here is actually airflow distribution.
Oh, because if it's uneven, you get hot spots.
Exactly. If the louvers aren't set perfectly, the trays in the middle stay totally wet while the edges overdry and just burn.
Which means your entire batch is ruined. And I imagine if you are a massive plant, you don't really have the time to constantly load and unload cabinets all day. You'd need something continuous.
Yes, and that leads us to the continuous tunnel dryer. So instead of a static cabinet, you have a long, heavily insulated tunnel.
Right.
Wet material goes in one end. It's usually layered onto a continuous screen belt or these moving trucks, and it slowly travels through various heated zones.
Ah, so it's moving the whole time.
Right, and by the time it reaches the discharge end, the moisture has been drawn out. The big advantage here is you can create specific temperature profiles.
Like blasting it with heat first and then cooling it down.
Yeah, exactly. You might hit the extremely wet material with high heat initially, and then lower the temperature near the exit just to prevent thermal degradation of the nearly dry product.
That makes sense for solids or thick pastes. But what about a liquid? I mean, if I have liquid milk and I need powdered milk, neither a tray nor a tunnel belt is really going to work. That brings us to the spray dryer, right?
Yeah.
Which, looking at the notes, looks like a massive multi-story silo.
Yeah, spray drying is such a fascinating application of surface area mechanics. So you pump a liquid feed into the top of this massive chamber and atomize it into a fine mist of tiny droplets.
Okay.
And then those droplets instantly collide with a stream of very hot air.
Wait, so a spray dryer is basically like sneezing into a hot hairdryer to instantly make powdered milk?
Huh. Well, the physics in that visualization are surprisingly accurate.
It works, right?
It does, because when you atomize the liquid, you are exponentially increasing its surface area. And the greater the surface area, the thinner the boundary layer of air around each droplet.
Oh, wow. So it's just much faster.
Instantaneous, practically. Heat transfers in instantly, and the water, the mass, transfers out just as fast. Then a drying process that takes 12 hours on a tray happens in about 3 seconds in a spray dryer.
3 seconds. That is wild.
Yeah. Then the dried solid particles just fall to a screw conveyor at the bottom, and the exhaust gas is pulled through a cyclone separator to, spin out and recover any of that fine escaping dust.
That instant evaporation is incredible. But to actually design any of these giant dryers, you have to deeply understand the air you are pumping into them. Because if your hot air is already saturated, like a muggy summer day, your dryer is essentially useless.
Completely useless.
You have to map the invisible water-carrying capacity of the air, which brings us to the entire science of psychrometrics.
Right. Without psychrometrics, you cannot calculate a drying rate. You are just flying blind. We can skip the basic definitions of relative humidity and thermometers, but we really must lock in the difference between dry bulb and wet bulb temperatures.
Okay, so dry bulb is just the normal temperature, right?
Exactly, the sensible heat of the air itself. Wet bulb is a completely different mechanism. If you take a thermometer, wrap it in a wet cloth, and blow air over it, the evaporating water pulls energy away from the bulb.
But cooling it down.
Right. And the temperature it eventually stabilizes at is the wet bulb temperature.
Let me think about the mechanism there. It's exactly how human sweat cools the skin. The sweat evaporating literally pulls thermal energy out of our bodies.
Yes, perfect analogy.
Mhm.
And at a certain point, it reaches an equilibrium. The heat transferring from the warm air into the wet cloth perfectly matches the energy leaving the cloth through the latent heat of vaporization.
And that balance is the wet bulb temperature.
Exactly. It is the temperature of the evaporating water itself, not the surrounding air.
That is a really critical distinction for the plant floor. Dry bulb is the air, wet bulb is the evaporating water. And to track all of this, engineers use the psychrometric chart. I remember looking at this in university. It looks like a chaotic spider web of intersecting curves and diagonal lines. It is incredibly intimidating.
Oh, it really is at first glance. It looks complex because it's graphing about 7 different thermodynamic properties simultaneously.
7.
Yeah, but I mean, you have to remember it is just a map.
Yeah.
And like any map, if you have 2 coordinates, you can find your exact location. You only ever need 2 known properties of your airstream to unlock all the rest.
Okay, let's take this map out of the abstract and put it into a real plant scenario from the source material. Say you are standing in a control room. Your standard thermometer, your dry bulb, reads 25 degrees Celsius.
Okay, 25 degrees.
And the relative humidity monitor reads 40%. It's a harsh winter day outside, and the window glass is sitting at 8 degrees Celsius. Are those windows going to fog up?
We can solve this instantly with the chart.
Yeah.
So you find 25 degrees on your horizontal dry bulb axis.
Right.
Then you move straight up until you intersect the sweeping curve labeled 40% relative humidity. That intersection is your exact state of the air. You are here, dot.
Got it.
But to find out if the windows fog, we need the dew point. That's the temperature where the air's moisture-holding capacity drops so low that water is just forced out of the air.
So from that intersection point, I follow the straight horizontal line all the way to the left until it hits the 100% saturation curve, right?
Yep, and when you do that, you hit 10 degrees Celsius. That is your dew point.
Okay, so the dew point is 10, but the window glass is 8.
Right, because the glass is colder than the dew point. The thin layer of air touching the glass drops below 10 degrees. It literally can no longer hold its water vapor.
So condensation forms immediately, the windows totally fog up.
Exactly. And, while a foggy control room window is annoying, this is actually a massive industrial issue. If you are venting hot, moist exhaust gas out of a continuous tunnel dryer and that uninsulated metal exhaust stack gets chilled by a winter storm.
The inside of your stack drops below the dew point.
Yes, it literally starts raining inside your exhaust pipes.
Oh, wow. Which can mix with process chemicals to form highly corrosive acids, right? Just eating your steel pipes from the inside out.
Yep, exactly. Understanding the dew point is literally how you prevent catastrophic equipment failure.
Okay, so mapping the air's properties is the foundation. But process engineers have to take it a step further. We have to calculate exactly how fast the water will jump from the wet solid into that air. This brings us to steady-state evaporation modeling.
Right. The underlying intuition here is that evaporation is a dual synchronized dance. It is heat transfer and mass transfer happening simultaneously. You can't separate them.
Okay, so heat pushes in, mass pushes out.
Exactly. The rate of heat pushing in from the air provides the latent energy required to vaporize the liquid. And the rate of mass transfer is that newly formed vapor physically moving away from the surface into the bulk airstream.
But the notes highlight a pretty counterintuitive rule for this to actually occur. The air blowing over the solid could be like 100 degrees Celsius, and the wet solid could only be 30 degrees Celsius.
Right.
Heat is obviously transferring in, but evaporation doesn't depend on that temperature difference. It depends on vapor pressure.
That is the core driver. For drying to actually occur, the absolute humidity directly at the surface of the wet solid must be greater than the humidity of the bulk air blowing over it.
Because mass moves from high concentration to low concentration.
Yes. So if the bulk air is already completely saturated, I mean, no matter how much heat you pump in, the water has nowhere to go.
Let's talk about the math behind this dual dance, but let's try to avoid reading an alphabet soup of variables. Conceptually, how are we calculating these two rates for the exam?
Sure. So the rate of heat rushing in is driven by the temperature difference between the hot air and the cooler wet surface.
Right.
And that difference is scaled by the total surface area exposed and a heat transfer coefficient, which is essentially measures how easily heat punches through the thin boundary layer of air surrounding the product.
Okay, and the mass transfer side of it.
The rate of mass leaving is driven by the humidity difference, the high humidity at the product surface versus the lower humidity of the bulk air.
So same basic structure.
Exactly. This is also scaled by the surface area and mass transfer coefficient, which measures how easily water vapor diffuses through that same boundary layer.
And because this is a steady state process, those two equations are permanently linked.
Yes. The heat going in divided by the exact amount of latent energy required to vaporize one drop of water perfectly equals the mass coming out.
But calculating those coefficients, the heat transfer coefficient and the mass transfer coefficient, seems like a nightmare. Are engineers just like looking these up in massive reference tables every time the air temperature changes by a single degree?
Well, sometimes. But more often, we rely on a brilliant piece of physics called the Lewis relationship, or the heat and mass transfer analogy.
The Lewis relationship.
Yeah. It turns out that for an air-water system, the way thermal energy diffuses through the air is mathematically almost identical to the way water vapor molecules diffuse through the air.
Wait, really? The physical movement of heat and the physical movement of molecules face the exact same resistance?
Yes. The ratio of thermal diffusivity to mass diffusivity is called the Lewis number. And for humid air, it is approximately 1.
Oh, wow. So they just cancel out.
Pretty much.
Oh.
This gives us a massive mathematical shortcut. It means the mass transfer coefficient is directly equal to the heat transfer coefficient divided by the humid heat capacity of the air.
And humid heat is just the specific heat of the dry air plus the specific heat of the water vapor it's carrying.
Exactly.
That is incredibly elegant. You just calculate the thermal properties of the air and it immediately hands you the mass transfer properties. But looking at this, I see a trap in this steady state modeling.
What's the trap?
To calculate the heat rushing in, I need the temperature difference between the air and the wet surface. But to calculate the mass rushing out, I need the humidity at the wet surface. Both equations require me to know the exact temperature of the wet product surface. What if I don't know it?
This is perhaps the most common challenge in both exams and real plant design. You have one unknown variable holding up two coupled equations.
So what do you do?
The only way forward is to iterate. You must make an educated guess of the surface temperature.
Let's walk through that with an example from the slides. Say we are drying wet clothes on a line. The air is 20 degrees Celsius, 60% relative humidity. I guess the surface of the wet fabric is 18 degrees.
Okay, so with your guess of 18 degrees, you go to your psychrometric chart and find the saturation humidity at that exact temperature.
Right.
Then you plug that into your mass transfer equation to see how much water should be evaporating. Then you plug your 18-degree guess into your heat transfer equation to see how much heat is arriving.
And since they are a dual dance, if the heat arriving doesn't provide the exact amount of energy needed for the mass evaporating, my guess is wrong.
Yep. And you guess again. You basically adjust your surface temperature up or down until the two equations perfectly balance. And that balanced temperature is reality.
Okay, this brings us to the ultimate curveball in the source material. The assumption we've been operating under this whole time is that heat is only arriving via the hot air blowing over the object. Pure convection.
Right.
But what happens if the tray the wet material is sitting on is an active heat source, like a solid metal tray?
This is where the physics shift, and honestly, where students routinely drop exam grades.
Oh boy. Let's break it down.
If you are using a mesh tray where air just flows through, or a spray dryer where droplets are suspended in midair, the only heat source is convection.
Okay.
In that strict, isolated scenario, all the heat goes into evaporating the water. Therefore, the surface temperature of the product exactly equals the wet bulb temperature of the air.
Because the evaporating water is constantly cooling the surface down to that wet bulb equilibrium point.
Exactly. Consider what happens, however, when you add a second heat source. Let's say you place your wet solid on a solid metal tray that is sitting on a heated rack.
So now we have convection from the air above, plus conduction from the metal tray below.
Yes. Heat travels rapidly through the metal, which offers very little thermal resistance, and it pushes up into the wet solid from underneath.
Let me make a logical leap here. The evaporating water at the top surface is trying to pull the temperature down to the wet bulb point. But now there's a massive pool of extra energy flooding in from the bottom.
Right.
So the water is evaporating as fast as it can, but it just can't keep up with the extra heat flux.
That is a perfect deduction.
Yeah.
Because there is extra thermal energy feeding into the system that isn't originating from the air, the equilibrium shifts. The surface temperature will be pushed higher than the air's wet bulb temperature.
Okay, so the golden rule here. Pure convection only means surface temperature equals wet bulb. Multiple heat sources means surface temperature is strictly greater than wet bulb.
Spot on.
And looking at the notes, you can push this even further by adding thermal radiation, like if you stick it in an oven.
Yes, and this is where the math gets heavily involved. If you place that metal tray into an oven with, say, glowing heating elements above it, you now have convection from the air, conduction from the bottom tray, and thermal radiation from above all happening at once.
Wow.
To solve this, you have to use the Gain-Complice equation, which sums up all these distinct heat resistances into one overall energy balance, and you iterate again to find a new, much hotter surface temperature.
So we've broken down the hardware, the air mapping, the mass transfer analogies, and the multiple heat sources. Let's bulletproof the listener's knowledge. What are the most common mistakes you see when people try to apply these formulas on exams or in actual plant design?
Well, the most fatal exam mistake is forgetting that thermal radiation calculations must absolutely use the Kelvin temperature scale, not Celsius.
Oh, because of the specific law it uses.
Right, radiation is governed by the Stefan-Boltzmann law, which relies on absolute temperature to the fourth power. If you plug 20 degrees Celsius into that equation instead of 293 Kelvin, your result isn't just slightly off. It is catastrophically wrong.
That is a very harsh way to fail a test. What about unit mix-ups? Any common traps there?
Misinterpreting the units for absolute humidity is a chronic issue. Absolute humidity, the X on your psychrometric chart, is strictly the mass of water vapor per kilogram of completely dry air.
Dry air, got it.
However, a problem might state you have an 80% moisture solid product. That means you have 4 kilograms of water per 1 kilogram of dry solid.
Right.
Students frequently try to plug the solid's moisture ratio into the air's humidity equation, and they are entirely different physical states.
That makes sense. And what about out in the field? What's a classic plant operations mistake?
Definitely failing to account for dynamic weather conditions when operating a continuous tunnel dryer that draws in outside air.
Oh, because the starting air changes.
Exactly. If a cold front rolls in or a sudden thunderstorm spikes the ambient humidity, the starting condition of the air entering your heaters has fundamentally changed.
So you have to constantly monitor it.
Yeah, if you don't use your psychrometric chart to adjust your heater temperatures or fan speeds in real time, your exhaust drops below the dew point. Or worse, your product comes off the conveyor belt, still wet, just ruining the entire production schedule.
All right, we have covered a massive amount of highly technical ground today. Let's transition to the rapid review and final quiz to really lock this entire deep dive into your memory. Let's start with the spoken revision checklist. What are the mandatory concepts the listener needs to walk away with?
First, know your dryer mechanisms. Tray dryers for batches, tunnel dryers for continuous profiles, and spray dryers for instant powdering via maximized surface area.
Got it. And the psychrometric chart.
Right. Second is master the psychrometric chart. Remember, it's just a map. You need 2 known points to find your intersection, and from there you can trace lines to find the dry bulb, wet bulb, absolute humidity, and dew point.
Perfect. Third on the list.
Third, memorize the physical meaning behind the Lewis relationship. It proves that the mass transfer coefficient is directly proportional to the heat transfer coefficient divided by the humid heat.
Okay, and the fourth.
Fourth is the golden rule of multiple heat sources. Pure convection means surface temperature equals wet bulb temperature. Add conduction or radiation, and surface temperature will be greater than the wet bulb temperature.
Excellent. And where are you actually going to use this in your engineering career? Let's go over 5 real-world submissions.
Okay, 1, designing atomization parameters for spray dryers in the milk powder or pharmaceutical industries.
2, troubleshooting unwanted acid condensation inside process plant exhaust stacks by calculating dew points.
Right. 3, calculating the required residence time of wet paper traveling continuously over heated mesh trays.
4, optimizing the global transport weights of harvested raw materials by engineering the most energy-efficient water removal process right at the source.
And 5, specifying the airflow rates required to dry granular chemical feeds continuously on screen belts without accidentally fluidizing the bed.
Awesome. Now, if you are facing a university mass transfer exam, here are 5 highly likely questions you should be prepared to answer based on these notes. Let's list them off.
Number 1, define wet bulb temperature versus dry bulb temperature in terms of latent and sensible heat.
Question 2. Given a dry bulb temperature and relative humidity, use a psychrometric chart to find the precise dew point.
3, calculate the mass transfer coefficient of a system by utilizing the heat transfer coefficient and the Lewis relationship.
Question 4. Explain the iterative mathematical process for finding an unknown surface temperature when setting the heat transfer rate equal to the mass transfer rate.
And question 5, will the surface temperature equal the wet bulb temperature for a wet solid drying on a heated solid metal tray?
And the answer to that, of course, is no. It will be greater due to the conductive heat flux. Okay, it is time for a short self-test quiz. You are in the hot seat listening to this. Think back to the start of our discussion. If the control room of your chemical plant is 25 degrees Celsius with a 40% relative humidity, and a harsh winter storm has brought the window glass down to 8 degrees Celsius, what physically happens and why?
The answer is that the window completely fogs up. At 25 degrees and 40% relative humidity, the psychrometric chart tells us the dew point is 10 degrees Celsius.
Right.
Because the 8-degree glass is below that 10-degree dew point threshold, the boundary layer of air touching the glass can no longer maintain its vapor pressure, so the moisture condenses right onto the glass.
And that single scenario really encapsulates the entire dance of heat and mass.
It does. And I want to leave you with a final provocative thought to ponder. Knowledge is most valuable when you look at the macro-scale application. Globally, we spend gigawatts of power just burning immense amounts of fossil fuels, simply heating air to force water out of industrial products.
Right. It's hugely energy intensive.
But the next time you look at a simple psychrometric chart, realize you are looking at the invisible, naturally occurring water-carrying capacity of the atmosphere itself. What if we could design next-generation industrial processes that perfectly harness that natural pressure differential, moving water from our products into the air without adding any artificial heat at all?
Wow. That is the exact kind of first principles thinking that completely redefines an industry. Huge congratulations to you for completing this deep dive into mass transfer, psychrometrics, and drying operations. Go print out a psychrometric chart, trace those intersecting lines, and visualize the boundary layers we discussed today. Good luck in your exams, and good luck optimizing those plant operations. We'll catch you on the next one. Picture a fresh, really plump grape sitting right next to a wrinkled little raisin.
Or imagine a giant rack of fish just baking under the intense sun in a coastal town.
Right, exactly. By simply removing water, we fundamentally change the physical nature of these materials.
We really do.
So welcome to the deep dive. If you're joining us today, you are probably on a mission.
A very specific mission.
Yeah, today's mission is to basically master process engineering drying operations, specifically mass transfer topics 6D, 6E, and 6F from the sources you've shared with us.
Right.
Our goal is to equip you with the deep intuition you need to not just, pass your engineering exams, but to actually troubleshoot real plant operations when you're out on the factory floor.
And to do that, we have to recognize that drying isn't just about, leaving something out in the heat and hoping for the best.
Right, it's not just hanging laundry.
Exactly. It is an incredibly delicate balance of heat transfer, mass transfer, and thermodynamics.
Wow.
Because if the engineering is off, you're looking at compromised product safety,
Yeah.
ruined shelf life,
Yeah.
or, absolutely massive wasted energy costs
Right.
in an industrial plant.
Okay, let's unpack this, starting with that grape. Why does simply removing water change a material so drastically?
Yeah, that's a good question.
And why is this considered one of the absolute most critical processes in chemical and food engineering?
What's fascinating here is that we actually have to stop looking at water as a simple single ingredient.
Okay.
We have to introduce the big picture concept that governs basically everything we are going to talk about today.
Right.
And that is water activity.
Water activity, denoted as
Yeah.
is sub, right?
Right. Water activity is a measurement of water availability. Mathematically, it is the ratio of the vapor pressure in a food to the vapor pressure of pure saturated water.
Wait, so water content isn't the same thing as water activity?
No, not at all.
Is it sort of like a bank account? Like your water content is your total net worth, but your water activity is the liquid cash that microorganisms can actually, withdraw and spend?
I actually love that analogy. Yeah, taking that a step further, you can have a solid that technically contains a massive amount of water molecules in its bank.
Like a high net worth.
Exactly. But if those molecules are chemically bound to the structure of the food, like hydrogen bonded to proteins or sugars, the bacteria can't spend them.
Because they're tied up.
Right, they are locked up in an illiquid asset. So a water activity of 0.9 means the vapor pressure is 90% of that of pure water.
Okay.
And the specific thresholds here really, really matter for engineering and safety. Fresh meat, fish, and raw vegetables sit way up at 0.99 water activity.
Which is practically an open bar for bacteria.
It basically is. The microbiological limits are super strict. To stop most gram-negative bacteria from growing, you have to drop that water activity below 0.97.
Just a tiny drop.
Right, but if you want to stop most molds, you have to get it down to 0.80.
Oh, wow. That's a bigger jump.
And the absolute toughest survivors, things like xerophilic molds that grow on dry foods or osmophilic yeasts that thrive in high-sugar environments, they won't stop growing until you drop the water activity down to about 0.60.
So that's the magic number.
Yeah, dried fruits like that raisin we started with typically sit right in that 0.60 to 0.65 range.
So as an engineer, your job is to manipulate that water activity. But you don't just have to physically evaporate water to get there, right? The sources mention you can drop water activity by adding solutes too.
Yeah, exactly. Adding salt or sugar chemically binds the free water, lowering the water activity without necessarily removing the moisture content.
Oh, like jams.
Right, jams or cured meats.
Yeah.
You can also freeze the material, or very commonly in industry, you combine methods.
Like doing two things at once.
Yeah, you salt a fish, which binds some water, and then you dry it, which removes the rest. That creates a massive cumulative drop in water activity.
That makes total sense.
This is a classic real-world engineering situation you'll face. Adjusting the sugar or salt concentration in the new recipe to hit a precise water activity of 0.80 to stop mold growth, but without turning the product into a literal brick.
Right, you still want people to be able to eat it.
Right.
So we know the why behind manipulating water, but how does that moisture actually physically fight its way out of a solid?
That's where it gets interesting.
Let's trace the journey of a wet material by looking at the classic drying curve. The one plotting moisture loss versus time.
Yeah, the drying curve is really the heartbeat of this entire topic. It's broken down into specific regimes. We start with regime AB.
Okay, AB.
This is the heating up phase. It's an unsteady state period where the solid's temperature and the drying rate are just adjusting, either increasing or decreasing.
Just trying to stabilize.
Right, trying to eventually reach a thermal steady state.
And once it hits that steady state, we enter regime BC, the constant rate period.
Exactly. And this raises an important question, right? Why is the rate constant?
Yeah, why doesn't it slow down right away?
Well, during regime BC, the surface of the solid is completely saturated. It's totally wet. As water evaporates from the surface into the air, it is continuously and immediately replaced by the internal movement of unbound water from inside the solid.
So the surface acts like just a puddle of pure water.
Basically, yes. The rate of heat transfer to the surface perfectly equals the rate of evaporation.
Oh, I see.
The physics are entirely governed by convective mass transfer from the surface to the air. For convective drying, the surface temperature of the solid is exactly the wet bulb temperature of the surrounding air.
Okay, the wet bulb temperature.
Right. So the drying rate during this period is completely dependent on external factors. How hot the air is, how fast the air is moving, and the humidity of that air.
Because the solid itself isn't putting up any internal resistance yet.
Exactly. It's just freely giving up water.
But that puddle is going to run dry eventually, right? What happens when the surface water is gone, and how does the water trapped deep inside the solid actually fight its way out?
So that turning point is what we call the critical moisture content, or X sub C.
X sub C.
Got it. This is a massive concept. At the critical moisture content, water is no longer freely available at the surface. The rate of internal water movement to the surface is suddenly less than the rate of evaporation.
The evaporation is outpacing the supply.
Exactly. And you can't just calculate this theoretically on a whiteboard. It has to be obtained experimentally.
Why is that?
Because it depends entirely on the pore structure, the thickness of the material, and honestly how fast you were drying it in the first place.
Okay, so crossing that critical moisture content plunges us right into regime CD, the falling rate period.
Right. The surface of the solid is no longer wet. The actual evaporating surface physically moves into the interior of the solid.
It retreats inside.
Yeah. Now, the rate of internal mass transfer controls the whole process. Because the water has to navigate a microscopic maze to get out, the drying rate progressively decreases over time.
And the mechanism depends on the solid's physical structure, right?
Yes, absolutely.
If the solid has open pores, it's controlled by capillary action, like water creeping up a paper towel. But if it's a fibrous or amorphous solid, it relies on diffusion, slowly permeating through the material itself.
You nailed it. And finally, we reach regime E, where drying basically stops.
The end of the line.
Right, the solid is at equilibrium with the drying air. To predict this final equilibrium water content for a known relative humidity of the air, engineers use sorption isotherms, which basically map out that exact relationship.
All right, the concepts are great, but the exam isn't just going to ask for theories. They're going to make us calculate exactly how long a batch takes to dry.
They definitely are.
Let's look at the math, which I know can be an absolute trap on audio. We aren't going to read out a long string of algebra, but we do need to understand the variables.
Yeah, let's focus on the proportional relationships and the formulas from topic 6e. For the constant rate period, the calculation is essentially linear.
Keep it simple.
Right. Your drying time goes up if your material is thicker or denser, or if you have a massive drop in moisture to achieve. That's the top half of the equation.
Okay.
But your drying time goes down if you pump in more heat, increase the surface area, or increase your convective heat transfer coefficient.
That makes intuitive sense. More heat, faster drying. More mass, slower drying. But the falling rate formula is a different beast entirely, isn't it?
It really is.
Because the drying rate is constantly slowing down as the water retreats into the solid, you can't just use simple algebra. You have to integrate across the drying curve, which introduces a natural logarithm.
Exactly. The variables remain similar,
Yeah.
thickness, density, heat transfer, but their relationships become nonlinear.
Yep.
We're calculating a curve.
Right.
And one of the most vital variables in this falling rate equation is the z factor.
Yes, the Z factor, the ultimate exam trapdoor.
It ruins so many exams. The z factor represents your drying surfaces. If you are drying material on a solid metal tray, moisture can only evaporate from the top surface.
Right, the bottom is blocked.
Exactly. In that case, z equals 1. But if you are drying on a tray with a perforated bottom, air hits the top and the bottom simultaneously. Moisture evaporates in both faces, so z equals 2.
Double the surface area.
Yeah. And if you forget that z factor, your calculated drying time will be off by 100%.
Let's actually put this into practice. Imagine you're standing on the factory floor.
Always a good place to start.
Right, or staring down a tough exam question. You've got a tray of wet sawdust in front of you, a layer exactly 2 centimeters thick.
Okay, 2 centimeters.
The tray itself is 2 square meters, and it has a perforated bottom. The initial moisture is 1.2 kilograms of water per kilogram of dry solid.
Got it.
You need to get it down to a final moisture of 0.5. The air blowing over it is 90 degrees Celsius at 10% relative humidity.
Okay, so before calculating anything, an engineer needs to identify the goal and the regime.
Right.
We need the time to dry. The situation notes that the critical moisture content for this sawdust is below 0.5.
So if our final target is 0.5 and the critical point is below that, wait, does that mean we never even hit the falling rate period?
Well, let's look closely at the parameters. Actually, if the final moisture is below the critical moisture, that's when you do enter the falling rate.
Oh, because you crossed it.
Right. But in our specific sawdust example from the source, if the prompt says the entire process is operating in the falling rate period, you immediately pull out the integration formula with the natural log.
Got it. And the physical setup is the crucial step.
Yeah, the prompt says it's a 2 centimeter thick layer on a tray with a perforated bottom.
Perforated bottom.
That instantly means our z factor is 2. So you plug z equals 2, your thickness as 0.02 meters. Always check your units and convert to meters, by the way.
Oh yeah, classic mistake.
Then you put in your dry density, your temperatures, and your moisture contents into that falling rate equation. The math is just plugging in the numbers, but the engineering is knowing which equation to use and identifying the physical reality of that z factor.
A 2 square meter tray of sawdust is great for a lab, but how do real factories dry thousands of kilograms of material? Let's scale this up and look at industrial dryer operations from topic 6F.
At an industrial scale, you have a few main workhorses. First is the tray dryer. This is a batch process. You load up trays, put them in a sealed enclosure, and fans blow heated air over them.
Pretty straightforward.
Very. But as an operator, your key physical indicator that the batch is finally finished drying isn't just setting a timer. You look at the exhaust air stack.
Because while the product is wet, the evaporating water cools the air down, right? So if the exhaust temperature is low, drying is still happening.
The physics bear that out perfectly. When the air outlet temperature rises back up to become close to the inlet temperature, accounting for some heat loss to the metal walls, obviously, and the outlet relative humidity matches the inlet relative humidity, it means no more evaporation is taking place.
The batch is done.
Exactly.
But if you're running a massive operation 24/7, you can't afford to stop and load trays all day. You'd use a continuous tunnel dryer.
Right. In a tunnel dryer, trucks full of trays or a continuous screen belt carrying granular feed move slowly through a long, heated tunnel. The crucial design element here is that the airflow is usually countercurrent.
Countercurrent, meaning they go in opposite directions.
Exactly. The fresh, driest, hottest air enters at the product exit.
So the driest air hits the driest product. Why do it that way instead of blasting the wettest product with the hottest air?
Because removing the last few percentages of moisture in the falling rate period is incredibly difficult. The water is trapped deep inside.
Oh, it needs more help to get out.
Right, you need the maximum driving force, the driest possible air, to pull that stubborn water out. The beauty of a continuous countercurrent process is that both your inlet and outlet temperatures and humidities remain completely stable over time, making it highly efficient.
But what if your product is a liquid, like milk or a pharmaceutical solution, and you need to turn it into a dry powder? You can't exactly put milk on a perforated tray.
No, that would be a huge mess.
That's where spray dryers come in, right? The liquid feed is atomized into thousands of tiny droplets inside a massive multi-story steel spray chamber.
Yeah, they are huge.
Heated air dries those droplets almost instantly, and the solid powder falls to the bottom, usually collected by a cyclone separator.
Spray drying is incredibly elegant, but it's also an operator's nightmare if the parameters slip. The critical variable in a spray dryer is the glass transition temperature of the material.
Okay, here is where things can get confusing. What exactly is a glass transition temperature, and why does it cause so much havoc?
Every amorphous material has a glass transition temperature. It's the exact thermal threshold where a hard, glassy solid suddenly softens into a rubbery, sticky state.
Why does it do that?
Because the molecules finally have enough thermal energy to just, move around.
Yeah.
So the air temperature inside the chamber, and therefore the product temperature, must be kept below the product's glass transition temperature.
So if you pump in too much heat to try and dry the droplets faster,
You exceed that temperature threshold. The droplets dry, but they become molten and sticky.
oh no.
Yeah, instead of a nice dry powder falling to the bottom of the cyclone, you get a hot syrup that coats the entire inside of the massive steel chamber.
That sounds like a disaster.
It is. You aren't making powder anymore. You're making glue. You'll literally spend days chiseling it out of the equipment.
Over all of these machines, the trays, the tunnels, the sprayers, hangs the concept of dryer efficiency, represented by the Greek letter lambda, right?
Yeah, lambda. Efficiency is simply a measure of where your energy is actually going. The ideal situation is that 100% of the heat you pay for goes directly into the latent heat of evaporation.
Turning liquid water into vapor.
Exactly. Lambda is calculated as the mass of water evaporated times the latent heat, all divided by the total thermal energy input.
So what does this all mean for a plant manager? How do you increase lambda?
You insulate. You maximize the internal drying area compared to the external surface area of the dryer shell,
It's keeping the heat inside.
basically minimizing the heat loss to the ambient room. You want your energy hitting the product, not heating the factory floor.
Right. As we look at everything we've covered, I want to pivot to the practical takeaways. What are the biggest traps students fall into on exams, and what are the biggest mistakes engineers make in the field?
Well, on an exam, the single most common mistake is using the simple linear constant rate formula when the final moisture content actually dips below the critical moisture content.
They use the wrong math.
Exactly. If your final moisture is below X sub C, you must use the falling rate math or break it into two separate calculations if you start above and end below.
Makes sense.
The second trap, as we discussed, is forgetting the Z factor. Always, always ask, is this drying from one side or two?
And in the real world, out in the plant?
In the plant, the biggest mistake is confusing water activity with total water content when setting safety standards. You might think a new food product is safe because the total moisture percentage is low.
But it's not.
Right. If the water activity remains above 0.80, mold will inevitably ruin your entire production run. And, of course, ignoring the glass transition temperature in a spray dryer, which we just discussed, leads to catastrophic equipment clogging.
Yeah, the glue.
Yeah,
If we pull back and look at the 5 core pillars we've built today, it really paints a complete picture of process drying.
it does.
First, we established the absolute difference between water activity, which dictates microbial growth, and total water content.
Right.
Second, we mapped out the physical realities of the drying curve. The heating up phase, the constant rate where the surface is a wet puddle, and the falling rate where the surface dries out and water fights its way from the inside.
Yeah, and the third pillar builds right on that curve.
Mm.
It's grasping the difference between external mass transfer limits, which control that constant rate period, and the internal mass transfer limits like capillary action and diffusion, which control the falling rate period.
Fourth, we navigated the drying time formulas, focusing on proportional relationships and that crucial Z factor.
Don't forget the Z factor.
Never. And finally, the 5th pillar. Understanding how batch tray dryers, continuous tunnel dryers, and spray dryers operate differently, and how to track their efficiency, lambda.
Those pillars translate directly into the scenarios you'll face. Whether you are defining water activity to explain food safety to a client, sketching a drying curve to find the critical moisture point, or diagnosing why a batch tray dryer isn't finishing by checking the outlet air temperature.
Let's do a quick mental check, a little rapid review quiz.
Okay, lay it on me.
If you are adjusting a recipe, what water activity level do you need to hit to stop most gram-negative bacteria?
The data tells us you must drop it below 0.97.
Spot on. And what physical reality defines the critical moisture content?
It's the exact moment water is no longer freely available at the solid surface. Basically, the internal movement rate has become less than the evaporation rate.
Perfect. Finally, in the falling rate period equation, what does a Z value of 2 mean?
It means drying is happening from two sides simultaneously, like material sitting on a perforated tray.
Nailed it. If you've got those concepts locked in, you have all the tools, the math intuition, and the real-world troubleshooting skills for process drying.
I do want to leave you with a final thought to mull over.
Oh, sure.
In process engineering, we expend immense amounts of energy burning gas, generating steam, running massive fans, essentially fighting the fundamental thermodynamics of water, wanting to stay inside these physical structures.
It's a constant battle.
It is. So as you look at the energy efficiency of your plant, ask yourself a deeper question. Could we change the physical structure of the solid before we start drying?
What do you mean?
Could we mechanically press it or alter its porosity to literally shift the critical moisture content itself, rather than just blasting the product with more and more heat?
Wow. Something to think about next time you see a raisin. Thanks for joining us on this deep dive.